Question number 5. The question itself is okay, but there is something you probably need to pay attention. There is a reaction hidden here. What is the reaction? It's the sodium bicarbonate react with the sodium hydroxide to produce the sodium carbonate and water. Do I need to memorize this reaction? No. You need to interpret this question by yourself. So if we write it down into a net ionic equation by removing, the spectators, you will get a net ionic equation like this. So how to interpret this reaction? You can say this is the second step of the neutralization of carbonic acid. Because if you add base to carbonic acid, first it will be neutralized into bicarbonate. And then if you have more hydroxide, it will be further neutralized into carbonate because you neutralize the protons one by one. So this is the way how you interpret, the reaction. So with this in mind, I think B should make sense. Is B the correct answer? I remember because I just had a discussion with another teacher, this afternoon about this question. So I remember, B is the correct answer. But let's still have a look. First, we need to make the sodium 0.5 mole. So let's have a look. For sodium, it will be 0.20 plus 0.10 times 2 plus 1. 2 is here, 1 is here, right? And then divided by, what is the volume? 1 liter. So I think you are supposed to get, 0.5. And regarding the bicarbonate, since the sodium hydroxide will neutralize, the sodium bicarbonate, right? So let me see. Oh, B is not a correct answer. B is the incorrect answer because the sodium hydroxide is more than the choline here. Is A the correct answer? Is A the correct? Okay, good. Let's directly analyze the A. So I think you guys can work on the sodium plus, okay? I think this is pretty straightforward. We can skip it. We will focus on the bicarbonate. So we have 0.15 of sodium bicarbonate initially, and then there is 0.05 mole of sodium hydroxide, so which means by working on the subtraction, we will get the remaining sodium bicarbonate, right? And then divided by 1.0 liter. I think we should get 0.10, right? Did I solve your question? Okay, good. You guys can check the other options, but I think A should be the correct answer. What's next? Next is thermodynamics is fine. There are not so many questions. Next is kinetics, question number 30. Oh. Which changes will lead to an increase in the theoretical cell potential? Oh, sorry, I made a mistake. Number 30, not number 40. Okay. This is related to the rate law. I need to give you a brief introduction about what are the common used methods to derive the rate law. Basically, we have 3 methods. The first one is called rate determining step. I think this is very easy to understand, right? You just follow the slowest step, and then this step will determine the overall rate. The second one is called SSA. What is the full name of SSA? It's called steady states approximation. You guys can write down the following. The third method is called PEA. It's called pre-equilibrium approximation. And the second two are actually more commonly used. So here the question is asking which rate law are inconsistent with the proposed mechanism regardless of the relative rates of the two steps. So first, the common used assumptions is either the first step is slow, the second step is fast, or the first step is fast, the second step is slow, right? Although you may argue, can we have both steps fast or both steps slow? Definitely you can, but this is not a typical case. So a common used assumption is either first slow, second fast, or first fast, second slow. And then we are going to analyze these two scenarios. So now say first, the first step is slow, the second step is fast. So if this is the case, what kind of assumption we can make to the intermediate? We always focus on the intermediate, which means the production of the chlorine is very slow, but the chlorine atom, okay? But the assumption is very fast. So we will say the concentration of chlorine atom will remain in a very low value. Do you agree with this? Because it is produced slowly, and then once it is produced, it's quickly gone. It's quickly consumed by the second step. And then we can say the chlorine concentration is very low. And then we further assume the change, the dCl over dt is almost zero. What does this mean? Basically means over a certain period of time, you can assume the concentration of the chlorine atom doesn't change. And then we can further get the rate of production is pretty much equal to the rate of consumption. I'm talking about the intermediate, right? So which means we can write down, if this is K1, the backward direction is K minus 1, the second step is K2. So we will list all of the processes to produce the intermediate, which will be K1 times NO2Cl. This is the production. And then there are two processes to consume the Cl, right? The first is the backward reaction, which is K minus 1 times Cl. And then the second way is the second step, which is K2 times NO2Cl times Cl. First, that this equation makes sense to you guys? This is built on all of our assumptions. You're good? Okay, thank you. Let me know if you have any question, okay? Otherwise, it will be hard to follow because we have a lot of, work to do to solve this question. And then I think we can derive the expression of the concentration of the intermediate. I will later talk about why we want to know this, okay? So if we reorganize this one, you will get on the top is this, on the bottom is this. We just combine the two chlorine atoms here. Makes sense, right? So now we finally got the concentration of the chlorine atom. But why we want to work on this? Think about chlorine is the product, and only the second step produces the chlorine gas, which means we can use the production of the chlorine gas to express the rate of the overall reaction. So which means the rate of the reaction equals to delta chlorine gas over delta T. You can also use D chlorine gas over dt. They are pretty much the same. The only difference is D means the delta is very, very small. It's pretty much close to zero, right? This is some fundamental idea from calculus. And then how can we express the production of the chlorine gas? Because the chlorine gas is only produced in the second step, so which means the rate of the production of the chlorine gas equals to the rate of the second step, which will be this. Does this step make sense to you? We can use the second step's rate to express the rate of the production of the chlorine gas. And the rate of the production of the chlorine gas actually shows the overall rate because chlorine gas is the product, right? We can use the consumption of the reactants or the production of the products to show the rates. And then finally, we can substitute the intermediate. So this is why we need to figure out the intermediate by using our assumption first. And then if we put it in, we got K2, K1, NO2Cl squared over K minus 1 plus K2, NO2Cl. We got something like this, right? Obviously, this is quite complicated. It's not either 1 or not either 2. But since we have some assumption, our assumption is the first step is slow, the second is fast, which means we will have K2 is much greater than K1 and K minus 1, right? This is our assumption. The second step is fast. The first step, both the backward and forward reaction rates is supposed to be very slow. So if we have this, can we ignore these parts? We can, right? Because K2 times the concentration of the reactants is supposed to be much greater than the K minus 1. And then now it's clear. Finally, we can continue to cancel more stuff. Oh, finally, what do we got? We got this. So the final conclusion, the rate pretty much equals to K1 times NO2Cl, which gave us the first one, right? So what is the approximation we used here, guys? It's called steady state approximation. Which stuff is at steady state? Is the intermediate. The intermediate is at steady state. What does it mean? It means the concentration keeps the same during the time. It does not change, right? So this is the example of how to apply the steady state approximation. Later we can further discuss when should we use steady state, when should we use pre-equilibrium, okay? I missed a U here. And then let's have a look at our second assumption. I need to have more space. Okay, we are good. Make it slightly smaller. So our new assumption is here. The first step is a fast equilibrium because it's reversible, right? Fast equilibrium. The second step is slow, right? Then we can apply the pre-equilibrium approximation to the first step. What does it mean? So which means the consumption of the intermediate in the second step can be ignored because the second step is slow, right? So which means we can assume the first step is at equilibrium states since the second step is negligible, right? And then if the first step is at equilibrium, we can say the rate of the forward reaction equals to the rate of the backward reaction. Makes sense, right? And then we can say K1 times NO2Cl equals to K minus 1 times NO2 times Cl. And then we can further express the concentration of Cl equals to K1 times NO2Cl divided by K minus 1 NO2. And we also get the expression of the intermediate, right? And then the second step is slow, which means the second step is the rate determining step, and also is the only step to produce chlorine gas. The rate of the reaction equals to this, and equals to K2 times this, right? Follow the elementary reaction, and then we can put this in. We got K minus 1, K2, NO2Cl over K minus 1, NO2. And then let's have a look at our assumption. If the second step is slow, which means K1 and K minus 1 is much greater than K2. This 2 is cancelled, but seems like it's not working very well, right? That is the final results we get. Please correct me if I made any mistake during the process. I think now we are good, right? Oh, there is a square, guys. I apologize. Because there is already a NO2Cl here, right? Am I right? So we got something like this. So obviously, if you go back, in R2. So what we can choose, no matter what is the relative rate of the two steps, which one is always inconsistent, I think is the second one, right? Because the first one is consistent when we make the first assumption, which is here. So I will say the answer is B. Is the answer B? Okay, good. So as you can see, obviously, during the test, you won't use such a long time to focus on just one question, right? So my suggestion is you can skip it first. And then after you finish all of the others, if you still have time, you can go back. But I believe there must be an easy way for you to pick up the correct answer without deriving everything in this way, right? I believe so. But this is my way because I want to show you the full story, how we thoroughly analyze the question. Maybe you can just simply observe the first step and the second step. You can eliminate some of the options, right? Try it by yourself. Okay, so the next question is 28. Number 28. Oh, okay. This question is very interesting. I like this question actually. It's a combination of a little bit advanced math and also the understanding of the kinetics. First, you need to know both alpha decay and beta decay are first order, right? This is something you need to know. All of the decay are first order. The second one, you need to know the integrated equation of the Rayleigh law for first order reaction, which is supposed to be ln A equals to ln A0. A0 is the initial concentration of the reactants minus K1T. K1 means is a first order reaction. So based on this, we can further derive the equation of the half-life, which is ln 2 over k1. I believe this equation is provided in the AP exam. So, but in the USNCO, all of those equations are not provided. There are only 3 equations, right? But none of the 3 is this one. But guys, take some time to derive this equation by yourself, because half-life means A equals to half of A0. So you just need to do some math, and then you can get this equation, right? So go back to this question. The Bismuth 212 undergo both alpha decay and beta decay with an overall half-life of this much. So what is the half-life for the alpha decay? And there is a percent. There is a percent. So can we write down in this way? The rate of the overall decay equals to K alpha times the Bismuth's concentration plus K beta times the Bismuth's concentration, right? Because both are first order. So this is why the power is 1. And then we can combine the K alpha and the K beta, right? I will erase this part to give us more space. Okay, if this is the case, when we have the integrated equation, I think you will figure out the half-life will be ln 2 over K alpha plus K beta. I think it makes sense, right? Because you can assume this is the new K, and the K equals to K alpha plus K beta. So you put the new K here. You got the half-life in this way, right? So do we know the relationship between K alpha and K beta? I think we know, right? Because the K alpha over the K beta is supposed to be 35.9% divided by 64.1%. Does this make sense to you? Because this is the amount consumed at the same time. So obviously it's related to the K value. So now you know the T half. You don't know the K alpha and K beta, but you have 2 independent equations. Both are linear equations. So I think you should be able to solve both the K alpha and the K beta by yourself. Does this make sense to you? Okay. Next are 2 equilibrium questions. Question number 31 and number 34. Number 31 and number 34. First, let's have a look at question number 31. Ooh, it is a movable piston with a constant pressure, the system. The temperature is also constant. And then there is equilibrium. All of the reactants and products are gases. And then the delta H is positive, which means it's an endothermic reaction, right? So I think we simply interpret the information first. The question is asking which changes would decrease the number of moles of the reactants present in the piston at equilibrium. The first change is the temperature is increased. I think this is the direct application of Le Chatelier principle, right? The LCP. So according to LCP, if temperature is increased, how does the equilibrium will shift for an endothermic reaction? It will shift to the products, right? Because we want to reduce the change, which means we want to lower down the temperature increasement which will need to absorb some heat. So equilibrium shift to the right side. Obviously, this will decrease the moles of the reactants, so this is correct. The second one, a sample of argon is injected into the piston. This is a tricky question. So there is a movable, piston, and then the system is already at the equilibrium state, and now you put some inner gas, the argon, into the system. What will the system change? How does the volume change? Because this one is freely movable, right? The volume will expand, right? I think I need to make it more obvious. Put it here. Does this make sense to you? The volume will expand. And if we suppose the pressure is still the same, so the total pressure will equals to the pressure of the argon plus the pressure of the reactants plus the products, right? But keep this in mind, the total pressure is still 1 atm because the total pressure is maintained at 1 atm. It will always, at equilibrium with the atmospheric pressure, right? So which means when the argon is introduced, the pressure of the other stuff actually is decreased, right? So I think we can analyze this statement by using LCP. In LCP, if the pressure is decreased, this pressure is not the overall or the total pressure, it's the pressure of all reactants and products. If the pressure is decreased, it's all reactants plus products. If the pressure is decreased, how does the equilibrium shift? Exactly, right? It will shift to the right side with more moles of gases. So equilibrium shift to the right side. So which means the second, statement is also correct. I would like to provide another way for you to interpret the results. The volume expands, which means the pressure of all of the reactants and products decrease, right? So we will say, let's make a simple assumption, okay? Because the Kp equals to the PSO2 times the PCl2 divided by the PSO2Cl2. If we suppose the volume is doubled, okay? Let's say the volume is doubled, so which means we input the same mole of argon with all of the previous gases. And then the Qp, which is the reaction quotient, will equal to the PSO2 divided by 2. Does this make sense to you? Because the volume is double, which means the initial pressure is halved. And then times the PCl2 divided by 2. And then the PSO2Cl2 divided by 2. So which means it turned into the PSO2 times the PCl2 over the PSO2Cl2 times 1/2. Right? So which means it equal to the Kp divided by 2. Obviously, it's smaller than Kp. So if Q is smaller than K, and the final equilibrium should be Q equals to K, right? So the equilibrium should shift to the right side to increase the Q and make the Q approach to the K. This is actually how we explain when the pressure of the system decreases, the equilibrium will shift to the sides with more moles of gases, right? That is because the Q is decreased, right? Okay, this is this question. The next one is number 34. Number 34. I don't think 34 is very hard, but it's very easy to make mistakes. The KSP equals to the strontium times the hydroxide to the power of 2, which is this value, right? So if you write down the solubility equilibrium here, so initial is 0, 0, equilibrium, let's say it's x, this will be 2x. Does this make sense to you? And then the KSP equals to x times 2x squared equals to x equals to KSP over 4 cubic root, right? And then you can put the KSP here to solve the x. And then you use 2x to calculate the POH. And then finally you convert the POH into pH. So pH equals to 14 minus POH. I don't need to explain this, right? This is something, should be covered in AP Chem. So I think there are two places which will, make you make mistakes. The first is the 4 and the cubic root. The second place, finally, after, let's say, 5 minutes, I solved the x, and you forgot to times the 2. I believe there will be an option which will give you a correct answer if you just use x rather than 2x. So this is how USNCO designed the options, right? They will think about all of the possible, mistakes you guys will make, and then purposely provide the wrong options. I'm not sure. Did I answer your specific question? Since 3 of you, choose this question. Let me know if I didn't, fully answer the question. If you still have, further. Okay. Let's see. The next part is redox and the electrochem. Question number 40, the one we talked about before. Number 40 is not real calculation based. So what will increase the theoretical cell potential for a hydrogen-oxygen fuel cell? First, we need to understand the fuel cell is like this, right? A more efficient catalyst is used on the cathode. Think about it. Catalyst will speed up the reaction, but it will not change the delta H, the delta S, the delta G, right? And we know the cell potential is determined by the delta G, right? So if the delta G is not changed, which means the cell potential will not be changed. Think about catalyst is a stuff related to kinetics, and the delta H, delta S, delta G are all related to thermodynamics. So thermodynamics determine whether the reaction can happen, how much it can go to the right side, is it reversible or not, what is the equilibrium constant, if it is a battery, what will be the cell potential. All of those are thermodynamics. Kinetics deal with how fast the reaction is, what is the rate law, right? What is the mechanism, how to derive the rate law, how does the catalyst work here. Those are kinetics. So number 1 is incorrect. Number 2, the temperature is increased from, so this reaction obviously is exothermic, right? Because it is a combustion, it's a fuel cell, right? So no doubt it is an exothermic reaction. So temperature increment according to LCP for a exothermic reaction, how does the equilibrium shift? The equilibrium will shift to the left side, right? Shift back. So which means the E cell will decrease, right? Because if we shift to the left side, which means it has a less ability or less potential to finish the reaction, to reach the equilibrium, right? So this is why the second one is also incorrect. So the answer should be D. Let me know if it's not D. Okay. Guys, I think we already finished all of the questions with 3 votes. Congratulations to all of us. So we still have some time. We can either talk about some of the questions with 2 votes, or we can talk about other questions you guys are interested, or we can just end up earlier. Up to you guys. Let me get some water. You guys can think about what you would like to do, okay? I think we are pretty efficient. Is there any, specific question in this year you really want me to have analysis here by using the remaining, a little bit more than 10 minutes? Let's have a look. Oh, sure. I think this question shouldn't be very tricky, right? Basically, is the Lewis structure, right? So NO3, if you draw one of the resonance, I didn't show all of the lone pairs, okay? So I think the bond angle here is 120 because it's a perfect trigonal planar, right? NO2, you can draw several resonances. I only show one here. So there will be a lone pair here. I have to show the lone pair here, otherwise I cannot tell you the bond angle. So what is this bond angle, guys? Wait, how do you think the bond angle here? I agree with the 120. Why it should be less than 120? Yeah, the lone pair is larger in size compared to a bonding pair, and it's more repulsive, right? How to interpret the bonding pair is larger in size? Think about a bonding pair is attracted by 2 nucleus, so it's a little bit slim, and a lone pair is only attracted by 1 atom, so it's a little bit fat, right? So this one can give a larger repulsive force to the other bonding pairs. So this one is supposed to be smaller than 120. Fn2 should be like this. So this question is not very clear, I have to say, because those 3 bond angles are not exactly the same, right? So the question didn't specify which angle it's talking about, but in general, it's supposed to be around 120, right? And we should say these 2 bond angles, this bond angle is supposed to be slightly smaller because the double bond is fatter, right? And these 2 bond angles, these 2, are supposed to be slightly greater than 120, but the average is around 120. So based on this, I will say C definitely not the right answer because we even don't know which bond angle we are talking about. So finally, we have the NF3. So wait, so what bond angle here? So a perfect tetrahedral should give you the number you need to memorize, 109.5, right? That is a perfect tetrahedral. But similarly, there is a lone pair which squeeze the other three bonds, right? Which will make it smaller than 109.5. So I think we have enough reason to choose D as the answer, right? Yeah. You need to pay attention to the lone pairs. So this is why it's a good habit to show all of the lone pairs. Although sometimes it's time consuming. Okay, I'm done. Any other questions? Oh, go ahead. You're right. This is also a tricky question. USNCO likes to assess the exceptions. So if we change this question into which one release the greatest amount of energy, if the options is in between fluorine and chlorine, which one you will choose? Yeah. Which one? Uh-huh. So this is an exception here. The correct answer is chlorine. So although fluorine has the strongest ability to gain the electron, to absorb the electron, but it does not release so much energy because fluorine, the size itself is small. So when it gains one electron, it results in a large increment in electron-electron repulsion. So if you check the data, chlorine is the largest and fluorine is close, is second largest. So this is one of the typical exceptions in periodic trends. So this was assessed before, maybe in the local or 1 year of national power, I forgot. So this year, it slightly changed from the comparison between fluorine, chlorine into oxygen and sulfur. But it is the same strategy. So oxygen is small in size. So this is why sulfur has the greatest amount of energy. So, the size factor plays important roles in different situations. For example, let me give you one more example. Let's say hydrogen. Hydrogen has an atomic radius of 74 picometer. But if you check the size of the hydride, which is the hydrogen gaining one electron, this one is pretty much double. The size is pretty much double. I forgot the exact value. Why it increased so much? That's because the size itself of hydrogen is too small. So gaining one electron will increase the repulsion a lot, significantly. So this is why the hydride is so big. I remember the hydride has pretty much the same size as fluoride, which has much more electrons. So this is just a not so related example to show you the size matters.